Welcome to the ADVM 12, Unit 13, lecture on Profile by Todd Frazee. Introduction. Profile tolerances allow for precise control of a feature's form, orientation, and location by allowable variation within a specific zone. In this lesson, you will learn how to define line and surface profile tolerances and apply them to control variation either locally or across an entire feature. We will cover how to apply profile tolerances that extend all around a part or all over its surfaces, and how to complete and interpret profile feature control frames to achieve various levels of control, including composite and non-uniform specifications. Additional topics will include using profile to specify coplanarity, controlling conical surfaces, and applying dynamic profile tolerances. You will also sketch tolerance zones by creating different profile applications and explain the role of datum feature references in establishing constraints. Here are objectives. There's a whole mess of them here. So by the end of this lesson, you'll be able to define line and surface profile tolerances, apply profile tolerances to define allowable variation with a limited zone on a feature or across all of a feature, apply a profile tolerance to extend all around the profile of a part, apply a profile tolerance to extend all over a part to all surfaces, to complete profile tolerance feature control frames to achieve the allowable levels of control and combine them as needed, and draw a composite profile tolerance specification. We will also specify coplanarity requirements using profile tolerance, apply a non-uniform profile tolerance, identify profile tolerance as the means for specifying allowable variation on conical surface form, orientation, and location, apply a dynamic profile tolerance, and sketch tolerance zones created by each of the possible profile tolerance specifications and explain the constraints established by the datum feature references. Okay, profile specification. Line profile is the control of the line elements in one direction on a surface. Surface profile is the simultaneously control of all points across an entire surface. The same feature control format, but different tolerance symbols. And tolerance values is always at regardless of feature size. And diameter symbols never applicable to a form tolerance, this profile tolerance. And datum feature references as needed. Okay, so our two symbols, profile of a line and profile of a surface. Okay, we don't involve modifiers, so. Okay, profile tolerance using the feature control frames. The feature surface defined with a basic dimension. So in this case, we have the profile of a surface. It has a radius of 231 thousandths and a spherical radius that transitions to 225 thousandths. And we're controlling that shape between points A and B. Okay, so it's attached to the surface of the leader. Profile tolerance zone establishes the two boundaries defined relative to the true profile. Okay, the profile tolerance using general notes. A note typically excludes features with dimensional values showing directly applied plus and minus tolerances. and refine general profile tolerance through application of feature control frames shows smaller variation or form tolerance. Okay, line profile, or what used to be called profile of a line. It controls a single line element on a feature. Each element is independent from all others, and the controlled line elements parallel to the plane of control frame and supplemental geometry in a model. So think of like the hull of a boat, and it's supported by ribs that are cross sections along a surface. Profile line would be the perimeter of one of those ribs just in one section. So you have to control the tolerance between a range to just along one path along that feature, and it's perpendicular, it's parallel to the plane in which the dimension's actually called. And as it mentions in 3D models, you may have to have supplemental geometry to define where it falls. Okay, and the controlled line elements are parallel to the profile to which the tolerance is applied in orthographic views. So if we look at this to check it, you'd have to run an indicator over it following the same path, and it can't vary more than 12 thousandths in this case. Okay, profile of a surface, or surface profile. That expands on profile by simultaneously controls all elements of the feature, and all points on the surface must lie between the boundary centered on a true profile. So rather than it just being measuring one cross section, it's across the entire surface. Any given point needs to fall within range. Now, in practice, this is very difficult to measure without a coordinate measure machine or some sort of scanning technology. Okay, extent of application. Profile tolerances control the full extent of individual features to which they are applied unless otherwise indicated. Okay, and they may be necessary to clearly show the extent of the application when the extent of the feature is not obvious, and limit to extent within a feature or extend beyond a single feature. And supplemental geometry and notations are used in models. So the model itself's not enough. You'd have to have some geometry on there to tell you what zones, perhaps to measure where the limitations of the tolerance is. And notations are used in orthographic views, and there is an all-around profile or all-over profile symbol. Profile application across the feature. The profile tolerance application creates a tolerance zone across the entire feature. The extent of a feature may not be obvious, and limits of the application specified if any doubt. So if we look at our image on the left, or actually, I'm sorry, the right, we have a spherical radius of 250 thousandths with a profile tolerance of 3 thousandths. And if we look in the right side of the view, it simulates what that surface should look like. So the profile tolerance doesn't apply to the cylindrical part of the feature because it's pointed at one surface, and but you see this tolerance zone with these two phantom lines that are curved. That means that entire surface needs to be within 0.003 of theoretically perfect. Okay, profile applications between node and limits. Controls a single line element on the feature. So to clarify the extent of the application to avoid the risk of different interpretations, and it's used to specify when within the feature and specify when beyond one feature, and identify the tolerance extent with labels. So note between or from two symbols. So in the example here in the top, we have a model, and the one profile tolerance that's at the top goes between points C and D. Now those are not datums, those are the points that are flagged with leader lines. They still are referring to a datum A and B, which is the back flat planes of the part. Now there's another tolerance, so that profile tolerance of between C and D has to be held within 20 thousandths according to the tolerance. If we look at the second one, shifts to a concave shape, and between letters B and C, the tolerance is tighter at 10 thousandths profile tolerance. And then we move to what looks like a chamfer to a front leading edge, and between points edges B and A, the tolerance is looser again at 20 thousandths. And in the orthographic view below, it shows the same exact part, how it would be shown on a drawing. Okay, all around applications. Profile tolerance extends completely around the visible profile where the leader is applied in the orthographic view. All around is visible profile where a leader is applied in the orthographic views, and the all around the feature associates with the feature control frame in a model. It may label features if loss of associativity is a concern and does not indicate a requirement applicable to the entire part. So the symbol, it's very similar to the welding symbol for all around, and you put a little circle around the leader point, okay? And that means that you just point at the edge. In this case, they've got two. One of them is a 3 times all around profile of 20 thousandths, so that applies to the 3 slot features that are in this. And then the 30 thousandths all around applies to the outside perimeter. Your basic profile will be theoretically perfect, and then your range that it is allowed to deviate is the width that's called out in the tolerance block. Again, this is something difficult to inspect on the floor because you're assuming you know what theoretically perfect is without any dimensions. So this type of thing, unless there's a functional gauge made and inspected, say on a CMM, it's really difficult to check this kind of thing on the shop floor without probing and comparing it to a model. The all-over application is the profile tolerance applies to all features on the part, and applied with feature control frame or by a note, and every feature gets the same tolerance. It's applied with a leader pointing to any of the surfaces, and additional tolerance is applied to individual features to define additional requirements. I have seen this applied, and it's extremely difficult to control in a manufacturing environment. You're almost saying that everything has to be within one tolerance, and doesn't translate well to the shop floor. So if you're in an environment where you're able to CMM everything, you want to do 100% inspection, use this a lot. Otherwise, it's more practical to use other means to define this than just saying all around the entire model. And we still have basic dimensions to help define the profile, but oftentimes this type of surface to profile tolerance would be used with tabular data where you have a point cloud or a series of points that are being compared to a CMM model. Okay, individual radial elements. Okay, so the datum references are customized so that the primary datum only constrains rotational degrees of freedom, and it replaces past practice of using orientation tolerance for radial elements. So in this example below, we have this warped face. Looks like it might be a face cam type device, and you're controlling it radially profile across the surface within 5 thousandths according to this tolerance. Okay, profile tolerance boundaries. Tolerance zones are established relative to the true profile. The profile tolerances are used to establish bilateral or unilateral tolerance zones. The default is equally disposed, bilateral, centered on the true profile. Unequal disposed bilateral may be specified, and unilateral may be specified. The true profile does not establish a required manufacturing target unless otherwise specified. So here's the hard part. What is the true profile? Most measurement tools couldn't tell you. So again, you're comparing it to a model, or you've made some sort of form tool that's going to line up with your part, and you're able to measure deviation in the surface. Okay, here's an example of equally disposed bilateral profile tolerances. Okay, that is the default. So whatever the profile is, the tolerance is going to, of 20 thousandths in this case, would be distributed. It could be 20 thousandths, 10 thousandths per side of the edge line of perfect profile, as we see here. Other distribution of tolerance zones requires special indications in the tolerance specification. So this is the default. So that profile would have, a band around it that's 10 thousandths, and a band on the inside of it that's 10 thousandths, and your slots would need to, profiles would need to fit within those. And it's centered on the true profile of theoretically perfect of the part. And half the specified tolerance applies to each side of the true profile. Okay, unequally disposed profile tolerance. You have the U with a circle around it. It's specified when an unequal disposed profile symbol, and it follows the tolerance value following symbol defines the amount of tolerance zone that allows material to be added to the true profile. The true profile does not establish the required manufacturing target unless otherwise specified, and the risk of manufacturing variation violating the closer tolerance boundary as the required manufacturing target. Okay, so what this is saying is this profile can be 12 thousandths, up to 12 thousandths larger than the profile, and it can be up to 8 thousandths smaller than the profile, and that's why there's two numbers separated by the U symbol and so it is not proportionally sharing the tolerance that goes around the inside rim of this snap ring or whatever this is.